like to introduce our third speaker of the day, of the session rather, Jonathan Mace from Brown University, who's advised by Rodrigo Fonseca, is going to be speaking next on one of our 3 Best Paper Award winning papers. Jonathan is a 5th-year PhD student at Brown. He is going to be telling us about how to track causality across systems that could span multiple address spaces.
Thanks for the introduction. My name is Jonathan Mace. I'm a PhD student at Brown University. Pivot tracing is joint work with Ryan Roelke, who did his undergraduate at Brown. He could use some convincing to go somewhere to do a PhD, and my advisor, Rodrigo Fonseca. Pivot tracing is about dynamically instrumenting live distributed systems to get real-time statistics where we want to be able to correlate and group events across different processes, machines, and applications. And I'm going to begin my talk with an example just to make things concrete. So to begin, imagine you're operating a cluster running the Hadoop stack. A typical Hadoop deployment might comprise HDFS, the Hadoop distributed file system, HBase, a distributed database, and MapReduce, a data analytics framework. So let's add some users and workloads. Let's say we have 2 direct clients of HDFS, 2 HBase clients indirectly accessing HDFS, and 2 MapReduce jobs sorting data that resides in HDFS. In this scenario, how might you go about monitoring the cluster's disk usage? Well, HDFS is a reasonable place to start because it's our underlying file system, and it conveniently has data node metrics, which track disk read and write throughput on each machine. If you ran the setup that I described, as we did, then you'd be able to plot disk throughput over time, grouped by machine like this. But what if you wanted to attribute disk consumption to the applications sitting on top of HDFS? HDFS doesn't provide such a grouping, and it doesn't report its disk consumption statistics back to its clients. With pivot tracing, we can capture this kind of grouping. We plot the data here in this figure, where you can see the throughput attributed to the applications on top of HDFS. But let's suppose now you're interested in disk throughput grouped by top-level client application. This is a particularly useful grouping because it tells you which users and workloads are the ones that are ultimately responsible for consuming the disk. But for the same reasons as before, HDFS doesn't provide this grouping because it doesn't have visibility into the other applications that are running on the cluster. With pivot tracing, we can query this, and this figure shows the HDFS throughput grouped by top-level client application. But our original question was about how disk bandwidth was being used across the entire cluster, not just from within HDFS. Data node metrics will miss, for example, the intermediary disk accesses made by MapReduce. So where else could you get disk metrics from? Well, typically cluster managers might expose disk statistics broken down by process, and an equivalent strategy here would be to instrument Java's I/O streams, since these are all Java processes, to capture all the disk consumption. In this scenario, you would be able to capture all of the extra disk consumption made by these other processes, but now you would lack the visibility within the processes. Ideally, you'd want to capture all of this disk consumption while still attributing it to the top-level clients. This figure shows not only which top-level applications are, top-level clients are responsible for disk accesses, but also from which processes. So in the rest of my talk, I'll show how pivot tracing can obtain and correlate these metrics, as well as any others from arbitrary points within the system or across the cluster. We'll also come back to this example at the end, and I'll show how we used pivot tracing to uncover a bug in HDFS that was seriously affecting the FS read workload. But before I do that, there are 2 important reasons why doing this is hard today. The first reason is that today, logging and monitoring tools are incorporated into the system at development time. So we have to decide a priori what to log and monitor. When we encounter problems in a deployed system, the logging and monitoring tools often don't have the right information to diagnose a problem. And simultaneously, they probably have a lot of irrelevant information. If the user needs information that the system doesn't currently expose or wants to break information down by different groupings, then they're going to have to go back to the developers or patch the software themselves. And then we have to consider whether it's worth the cost of adding this additional instrumentation to solve a problem that most users won't need. We found ample evidence of this in various issues on Apache's issue trackers, where users are requesting additional instrumentation or different breakdowns. For example, this JIRA here from HDFS's issue tracker is just requesting a simple breakdown of HDFS usage by user and group, very similar to what I showed earlier. But this remains unresolved after more than a year. The second reason why this is hard to do today is that we often want to correlate information from different services and applications, and there are myriad ways to break down and group even just a single metric. As we saw with the HDFS disk metrics, it can't account for all of the different ways that an operator might want to break down or group it. Correlating events across multiple systems is especially difficult when systems are designed to compose, because it turns out that it's rare that the systems embed monitoring that relate to other services. Like, consider Netflix's microservices Death Star. Here, the global configuration is constantly changing. Dependencies aren't going to be known in advance, and neither are the questions or correlations that are asked by users and operators. Pivot tracing addresses both of these challenges by combining two key techniques. We use dynamic instrumentation so that we can defer until runtime our choice about what to monitor, and we use techniques from causal tracing so that we can correlate events from different points in the system at runtime. A natural way to expose these two features is to first model system events as the tuples of a streaming distributed dataset, over which we can dynamically evaluate relational queries. Second, in order to express causality, we introduce the happen before join operator, which joins tuples based on Lamport's happen before relation. With the happen before join, we're subsequently able to group and filter events based on the properties of any events that causally precede them within an execution. While these are general concepts that can apply to any distributed systems, for concreteness, I'll be presenting pivot tracing in the context of our Java prototype and the Hadoop stack. So let's take a look at how pivot tracing works. In our previous example, we were looking at data node metrics in HDFS. Then we view each literal invocation of this increment bytes read function as a tuple containing features of the event, such as the name of the function invoked, the values of local or global variables at that point in time, the host name of the machine, a timestamp, and so on. In the tuple shown here, for example, we have the value hop01 for the host and the value 10 for delta. As an example of how pivot tracing expresses relational queries over this dataset, the very first figure I showed, plotting disk throughput by host, can be expressed as this query, which takes the tuples produced by the increment bytes read function, groups them by host name, and then outputs the sum of the delta variable for each group. We use the term trace points to refer to these places in the code where pivot tracing can add instrumentation. A trace point will specify, for example, a class and method signature, like in aspect-oriented programming, and it exports several variables that queries can refer to. But key to pivot tracing is the ability to correlate with events that occur elsewhere across the system. In order to produce this graph, we had to relate the data node metrics event with the client process that initiated the request. The happen before join enables us to express this sort of relation with which we can write queries to join tuples produced by multiple trace points. So just to give an example, suppose a request first passes through the client protocol's trace point, producing a tuple containing, among other things, the client process's name hget, then subsequently passes through the data node metrics trace point, producing a tuple that contains the value 10 for delta. With the happen before join, since these two invocations satisfy the happen before relation, a happen before join between client protocols and data node metrics would produce a tuple that contains all of the values from both trace points, in this case, both hget and 10. So now we can write a query that joins every tuple, every pair of tuples from client protocols and data node metrics that satisfy this happen before relation. And to briefly explain what this query does, we select the tuples produced whenever data node metrics is invoked. We perform a happen before join with earlier tuples produced by the client protocol's trace point. We group the results by the process name from client protocols. Then for each group, sum up the values of the delta variable. In the example shown here, the query would produce a tuple containing the name hget and the value 10. So pivot tracing overcomes the aforementioned challenges by utilizing two components. First, queries are dynamically installed into a system at runtime using dynamic instrumentation. And to do this, a system needs to add a pivot tracing agent in order to perform this dynamic instrumentation. And second, a system needs to support our baggage abstraction. Baggage is what enables us to implement the happen before join and thereby causally relate events from different parts of the system. And I'll briefly look at baggage now. Specifically, baggage is just a key value container that's propagated along the execution path of a request. It's a generalization of the metadata propagation techniques that have been used in previous causal tracing work. And it's implemented at the granularity of an individual request within a workload. With baggage, we can propagate state alongside a request for use later. For example, if we have two trace points A and B, then at trace point A, we can put the client name fsread into the baggage. Then later at trace point B, we can get the client name from the baggage, and we'll get back fsread. This combination of a pivot tracing agent to perform dynamic instrumentation and baggage to do metadata propagation is what we need for a system to support pivot tracing. But with this, I'll walk through the steps that pivot tracing takes to evaluate a query. So we start with our instrumented system and the users of our system submitting workloads. And as introduced earlier, we have several trace points defined that refer to places in the code where pivot tracing can add instrumentation. Here I've highlighted trace points A and B as examples. Trace points export identifiers for variables in the code that queries can refer to, as well as several default variables such as the host name and the timestamp. Trace points are only references to locations in code. They're not baked into the system, and they don't require a priori modifications. They can be considered like recipes for how to instrument the system. And defining and using trace points isn't difficult. People do this sort of thing today with systems like dtrace. Now we can write queries about the values exported by trace points. Pivot tracing's query language is a simple relational query language like SQL, but more so LINQ. Here, this user is performing a happen before join between A and B. This query groups by process name at trace point A, then sums up delta from trace point B. The output of a query is a stream of tuples over time. So users submit queries to the pivot tracing front end, which compiles the query into advice, an intermediate representation of the instrumentation needed to evaluate a query. Advice is ultimately installed in the system at the trace points referenced by the query. And advice has a limited instruction set. All it can do is observe the values of trace point exported variables, pack values into the baggage, filter out unwanted values, unpack values, and emit tuples for global aggregation. So the pivot tracing front end then sends the advice to the pivot tracing agents, which dynamically add the advice to the requisite trace points. We call this process weaving. So from here, let's look at how the happen before join is then evaluated. When a request passes through trace point A, the advice A1 will be invoked. This will observe the process name and pack it into the baggage. Subsequently, if the request passes through trace point B, the advice B1 will be invoked. This will observe the value of the delta variable, unpack the previously packed process name, and emit an output tuple. If there was no process name in the baggage, then nothing is emitted, because that implies that we didn't go through trace point A. Since baggage explicitly follows the path of a request while it executes, happen before join is just evaluated in line with the request, avoiding a costly global evaluation. And in this demonstration, I was using a simple serial request as an illustration, but in the paper, we outline how to evaluate happen before join in the general case for executions that arbitrarily branch and rejoin. So finally, the local pivot tracing agents aggregate output tuples locally, and they periodically publish them back to the pivot tracing front end and back to the user. So we implemented a prototype in Java and evaluated it in the context of the Hadoop stack. Our prototype has the following components. First, we have an agent thread that runs inside each pivot tracing enabled process. The agent implements the advice API and uses JavaSys to dynamically rewrite and reload classes. We use a simple pub subsystem to receive weave commands from the front end and send back tuples produced by the queries. We implemented a baggage library with a straightforward API. The data format is specified using protocol buffers, so baggage can be propagated between systems written in different languages. And our baggage library uses thread local storage within a process and then has methods for serialization to include the baggage in remote procedure calls. Finally, we implemented the pivot tracing front end for writing queries, compiling them to advice, and submitting them to the pivot tracing agents. The front end implements several query optimizations that we outline in the paper that let us push operations close to their source. We instrumented several systems in the Hadoop stack with pivot tracing, each of which only required about 50 to 200 lines of code per system for adding baggage. And primarily, this is at the boundaries of execution, passing baggage between threads or including it in RPC invocations. And this is a one-time modification as a prerequisite for supporting pivot tracing. With pivot tracing enabled, we recorded a baseline overhead of only 0.3% in application level benchmarks when there were no queries installed. And this is low because baggage propagation alone is relatively cheap, and there's no overhead for queries or trace points until after they've been installed. On the same application level benchmarks, we recorded a maximum of 14.3% overhead incurred for queries from the paper. And this benchmark represents the worst case possible, where requests were sub-millisecond, CPU-only, lock-free lookups. And of all the queries in the paper, the largest baggage size was only about 137 bytes. In the paper, we demonstrate pivot tracing in 3 different kinds of scenario. First, pivot tracing can relate arbitrary metrics from one point in the system with identifiers meaningful elsewhere. The figures I presented earlier in the talk are examples taken from this demonstration. So for many types of queries, the overhead is sufficiently low that long-lived health monitoring can be implemented using pivot tracing. Second, pivot tracing can measure latencies by using the timestamps from 2 or more trace points. We diagnosed a limping hardware problem that was affecting end-to-end request latencies. And finally, pivot tracing can be used to debug recurring problems in distributed systems, where the kinds of debugging information we need is very specific to the problem, and it's unlikely to be included in existing system logs or metrics. I'm going to present this problem here now, and I'll refer you to the paper for details on the other 2. And to describe this problem, I'll outline a sort of scenario, and we'll come back to HDFS, which I'll describe in just a little bit more detail. HDFS comprises a central name node that stores the file system metadata, and several data nodes that store the data of the files. To store a file in HDFS, it's broken up into blocks that are replicated across the data nodes, and the HDFS name node maintains the mapping from files to blocks and their locations. So here I'm showing that the file is replicated on data nodes 2, 3, and 5. To look up a file, a client first contacts the HDFS name node to find out which data nodes have the file, and it invokes a name node procedure called getBlockLocations, passing the file name and getting back the list of replicas. Subsequently, the client selects one of the replicas according to HDFS's replica selection policy. The goal of the policy is to minimize network load by selecting topologically close replicas. So first, if the client is running on the same machine as a data node that has a replica, it'll read that local replica. Second, if there are any replicas on the same rack of machines, then a random rack local replica will be selected. The policy uses randomization to break ties in order to spread load. Finally, if there are no local or rack local replicas, then a random off-rack replica will be selected. Once a replica is selected, the client contacts the replica to read the file. The client invokes the data node's data transfer protocol, which subsequently returns the contents of the file. So in this scenario, I was setting up an 8-node cluster with a simple benchmark workload. This was actually happening just before the experiment that I presented at the start of the talk. I'd set up 8 identical machines, each running an HDFS data node and the same client workload generator that I wrote. The workload generators were just reading randomly from the same large set of files. We also had a name node running on a separate machine. So given that I was running the same simple workload on all of my machines, I was expecting to see more or less uniform throughput across my workload generators. But this wasn't the case, as I'm showing in this figure here. Each line is the throughput of one workload generator, and clearly there are two of the workload generators with consistently lower throughput. Furthermore, I was also expecting to see uniform throughput on the data nodes, since I'm just reading at random and files are distributed randomly. But in this case, the HDFS data nodes were seeing drastically different throughput. Each line here is the throughput of one data node. So clearly there's something very suspicious going on, and we'll walk through the steps of figuring out what it was. So my initial hypothesis here is just that the simple workload generator I wrote probably has a few bugs and isn't behaving as I intended it to. In particular, since the throughput was so skewed, I figured maybe I wasn't actually randomly selecting the files. So to debug this, I wrote a query to look at the HDFS name node and ask the question, which files are the ones that I'm actually looking up? So the query shown here simply counts how many times each file is looked up at the name node's getBlockLocations trace point. We can aggregate this over a period of time and plot a frequency distribution like this. And a binomial distribution is indicative that the files are being randomly selected for read. However, we specifically want this distribution for each client individually to make sure that each client is behaving correctly. So we can expand the query and write a happen before join with a trace point within each client. So what this does is it first joins the tuples from the client's trace point. We then add the client's hostname to the group by clause, and then include the client's hostname in the output tuple. This enables us to break down the output data by client, and then we can plot the same frequency distribution individually for each client. These distributions all have the same shape, which means that each client is indeed randomly selecting files. So this doesn't account for the problem that we were initially looking at. So maybe it's because the files themselves are skewed across data nodes. If some data nodes stored more replicas than others, then since we're reading files uniformly at random, that would likely lead to heavier load on some of those data nodes. So we're going to ask the question, how often is each data node a replica host? So we ran this query over a period of time and counted the frequency that each data node appears as a replica. This figure shows that barring minor variations, replicas are mostly distributed evenly across the data nodes. As with the previous query, we want to check that this is individually the case for each client. So just like before, we modify the query to join with and group by the client. And we can now plot the same result, but individually for each client, like this. And this result is still the expected behavior for HDFS. It's telling us that replicas are distributed evenly, and thereby this doesn't account for our weird throughput problem either. So clients are selecting files uniformly at random, and those files are distributed across data nodes uniformly at random. Yet the HDFS load is highly skewed. So perhaps the issue lies in the client's selection of which replica to read from. As mentioned before, the HDFS replica selection policy will perform a local read if it can, but otherwise it should randomly select a replica from the same rack of machines. So let's ask the following question. When a file is read from a data node, where else could it have been read from? To answer this, we'll write a query that relates the initial name node invocation of getBlockLocations with the subsequent invocation of data transfer protocol on the replica that the client ends up choosing and reading from. So this query performs a happen before join between the two trace points, then counts how often each pair occurs of candidate replica and actual replica. And just to make things more confusing, we're going to make our query a little bit more specific. We know that clients will try to first read locally, and we want to ignore that case. We only care about when the client's reading an off-rack replica and is having to choose randomly. So we're going to expand our query to also take into account the initiating client, and we're only going to produce tuples if the client's hostname is not the same as the ultimate data node's hostname. Okay, so we ran this query, and I'll pull up a figure in just a sec showing the query results. But before that, the result that we're kind of expecting to see is along the lines of the following. Whenever a client gets to choose between a replica on B and D, about 50% of the time B is selected, and 50% of the time D is selected. So I'm going to plot the matrix of replica selection preferences, starting with data node A. So this cell tells us that actually, when choosing between a replica on A and a replica on C, clients were selecting A 100% of the time, and they were selecting C 0% of the time. And following on with B, they were when selecting between B and D, they were selecting B 0% of the time and D 100% of the time. And as it turns out, there was actually a clearly preferred order of replicas, where A was the first preference, followed by D, then B, and so on. And this was a global ordering across the entire file system. And this really shouldn't be the case. I mean, this is terrible. We're supposed to be selecting replicas randomly, and this figure should be completely uniform. And it turns out that this was the cause for the weird throughput variations that we originally saw. What was happening was that the name node wasn't randomizing the replicas that it gave back to the client, and then the client was just selecting the first replica from the list. This led to high load on some machines and very little on others. So we didn't know about this bug before discovering it with pivot tracing. It turns out that another HDFS user had also discovered the bug, and since then it's been fixed in release 2.5 of HDFS. So this experiment demonstrates the kind of seamless correlations that pivot tracing can perform at runtime, even for very specific one-off metrics and groupings. The overhead of evaluating these queries was quite low. With all of the queries from the experiment installed simultaneously, we only imposed an application-level overhead of 1.5% on the workload that we were running. And that includes both the overhead of turning pivot tracing on and then evaluating the queries on top of that. So to conclude, with pivot tracing, we introduced the happen before join that enables queries to be contextualized by Lamport's happen before relation. Pivot tracing addresses the limitations of logging and debugging in distributed systems by combining dynamic instrumentation with causal tracing techniques to enable efficient evaluation of the happen before join at runtime. And the overheads of evaluating happen before join are sufficiently low that we believe pivot tracing is suitable for production systems, both for high-level standing queries and for digging deeper when necessary. So with that, I will conclude my presentation.
Jeff Kenning, Harvey Mudd College. So I really like the dynamic instrumentation. I've always been fond of being able to debug without having to recompile and things, or even write code. But I'm lazy. And so I was wondering, it seemed like your code to transfer package data is pretty structured, and I'm wondering if that could be done dynamically or at least automated.
So by this, do you mean the baggage?
I'm sorry, the baggage, yes.
Yep. So that's a really good question, because actually there isn't this tight coupling between pivot tracing and the propagation of this baggage. And there are other applications where you might want to use this metadata propagation. It's really nice to be able to propagate things alongside a request. So with pivot tracing, we only really supported simple data types. We actually packed everything as tuples, and the paper's a little bit more specific about how we do it. But we absolutely, definitely advocate for not tightly coupling things and just having this generic propagation of, I guess, bytes that can be interpreted by a tracing application that sits on top of the system. Does that answer your question?
I was just wondering, how structured is it? Is it amenable to automation, or is it really going to have to be done by hand for every system?
Oh, so do you mean actually implementing the propagation of the baggage in the system?
Yeah.
I'm very sorry. I totally misunderstood the question. So I get asked this question a lot because I tell people that I instrumented a system in a day and they don't believe me. It turns out that, yes, most of it can be automated. The patterns for writing programs are typically not that complicated. Kicking off a new thread, putting a request into a queue, dequeuing something, running it for a bit, whatever. A lot of systems use these underlying frameworks for invoking RPC, for doing RPCs and that sort of thing. So the patterns can be automated. and we use aspect-oriented programming to instrument most of the general purpose patterns. And then after you do that, you can just record traces and see where they're not recording the things that you expect them to record. And I claim that it's really easy to then tie up the loose ends, and voila, you got your instrumented system.
Cool, thanks.
Hi, Mona Atarian from Google. I was actually wondering again about the baggage propagation. Did you need to make any kernel changes?
No. Baggage is stored and propagated entirely at the application level.
So I was wondering, if two threads of the same application, they communicate via signals, how would you be able
Sorry,
to?
could you speak up slightly?
If two threads communicate via signals, like one signal the other one to do something, how would you propagate the baggage?
Right. So if that's important, as in they're part of the same request, and this is part of the happen before relation within the context of the request, then my answer would be you need to do that. How would you do that? Would be up to the specific implementation. Maybe you would just have to copy the baggage, send the signal, and read the baggage, or something like that. That would be pretty cumbersome, but that's how you would do it.
Thank you.
Vasily Tarasov, IBM Research. Great work. So one of the great benefits of dynamic instrumentation is that you can postpone the decision on what to measure, what metrics to collect, and what analysis to do from the development phase to much later phases, what we noticed. And in the example that you gave in the beginning of your talk, the user goes to the developer, for example, in the old times to add a new instrumentation. With pivot tracing, however, the user still needs to know the class name, still needs to know the method, and even the semantics of the argument. So do you think this limits the application of this tracing just to the kind of development, but not to the to the people with good knowledge of the code, but not to the more immortals?
Well, my facetious answer to this would be, why would someone with zero knowledge of the code need to know anything about the internals of the code? But you're absolutely right. If you want to define a trace point, you need to know what the code is doing. There exist a lot of people who can look at the code and sort of glean what's going on. But the sweet spot really lies in the ability to just decouple the specification of these things with the development of the system. Now, this user who goes onto HDFS's issue tracker requests this thing, and some other user can come along an hour later and be like, here's a trace point that refers to the point in the code that you care about. If you had a system that you didn't want to expose the source to, you would still be able to export a catalog of these trace points, kind of like how dtrace works. And those would still be useful if you wanted to correlate with something in your application that you do know about.
Thanks.
Yeah.
We have time for one last question. You're welcome to take things offline. I don't want to delay the booster session.
Good, thank you. Mohammed Khatib, HGST Research. So I have a question about the metadata you collect, so to run queries against at the end for your tracing. How does it scale, with the number of nodes, for example, in your Hadoop system?
Right.
And how much gigabytes, terabytes you need to collect to really have some meaningful insight? Thanks.
So the latter question I'm not sure I can answer, because we didn't do large-scale analysis on the amount of data you need to collect to be able to answer these questions. But so the largest cluster that we ran pivot tracing on was a 400-node Azure cluster. And the scalability is, I'm going to make a bold claim and say that it's not an issue. Because the requests, if the requests are scaling up as you scale up your cluster, then pivot tracing is going to cost more, but then your requests are costing more. So it's not, the only place where the scalability matters is in returning the query results. And I guess the point of a lot of our optimizations in the paper are to really substantially minimize exactly what we're returning so that you're getting just the answers you need.
Okay, great, thank you.
Yeah.